All right. So welcome to the group 3 lecture number 5. So I think you had a tutorial, and let me just first ask if there are any questions coming from the tutorial. I will make some comments on it.
Sir, would you please explain why, how the D3, how to find the equivalence classes of D3 and D4? Like, I didn't get how to find class from a group.
Okay, so D3 and D4 would be similar. Let's just say, take D3. So D3 consists of the rotation element alpha, and then alpha squared, and then say alpha cubed is essentially E, right? And then we also have B, which is a reflection around one of the symmetry axes. And then we also have, say, B alpha squared. And we also have that B alpha is equal to alpha squared B, or the other way around. It could be that, alpha B is B alpha squared, right? So first thing to note is that, like E, this is always its own equivalence class, right? Let's call it E, right? Because, for whatever G you have, you're just going to get E, right? So, and you're not going to get any other elements in this equivalence class. So this is equivalence class number 1. Number 2 is that you want to say, okay, then pick an element which is not in this equivalence class. So we have a choice of picking this one, this one, this one, this one, this one. So we have 5 choices. Let's pick alpha. So let's pick alpha because it's not in the equivalence class that we have already established. And then we take all the elements of G and conjugate alpha. So what are these tries? So let's take, say, G to be alpha itself. Then what is G inverse? Can someone tell me?
Alpha squared.
Right, alpha squared. So then we have G alpha, G inverse. This is going to be alpha times alpha squared. But we know that alpha cubed, which is this thing, is the identity element. So this is alpha. So we see that conjugating by alpha does not give us any new element. Okay, so let's then start with try another. We go down the list of all the elements, and then we take alpha squared.
Is it like except alpha, we have to replace other elements in the G?
Well, also alpha, we also took alpha, right?
Yes, sir.
So we took G equals to alpha squared, and then G inverse is then alpha, right? And then G alpha, G inverse is going to be alpha squared times alpha alpha. So again, we get alpha. So none of these elements conjugating by alpha or alpha squared give me a new element. Now let's go and see what we can do with B. Okay, so if we basically take G to be B. If G is B, what is G inverse?
B.
Right. Then we get G alpha, G inverse is B alpha B. But we know that alpha B is equal to alpha squared B. Sorry, so B alpha squared, right? B alpha squared. This thing is equal to this thing. So this is going to give me B squared alpha squared. But B squared is 1, so this is alpha squared, right? So now we see that we are getting, in our equivalence class for alpha, let's call this equivalence class of alpha. Our first element was alpha. The second element is going to be alpha squared. Okay, now we can keep on doing this. Then G is going to be, say, after this, we are going to have B alpha, right? So G is going to be B alpha. Then what is G inverse?
B alpha square?
B alpha squared. Yes.
Alpha square B.
Yeah, I mean, you can write these things in many different ways using this commutation, this commutation relationship, right? So, so this is basically that relationship, non commutation here. So, Saif is like, okay, this is just a reflected version of a rotation, so that should be equal to this, right? That's how you Saif, you get it, right?
Oh yeah, but I actually put the square on just the alpha. I don't think that's correct.
Okay, let's see if it should, so you said B alpha squared, right? And let's see if that works. G inverse is B alpha squared. But this is B alpha squared. So this is 1. Then we have alpha, right? So this is, yeah, this is not equals to identity. So that's not going to work. So so this is going to be Farhan, what did you say?
I said alpha square B.
Alpha squared B. Okay. Farhan said alpha squared B. Let's try that. So this doesn't work. G inverse is B alpha squared B. Now alpha squared is 1. Alpha squared is 1, and then we have B squared, which is 1, right? Seems like that's good. Yeah. So now if I use this, then G alpha, G inverse, G is B of alpha, and then alpha squared of B, right? So here we have alpha cubed, and alpha cubed is giving me 1. So B, the identity. So, sorry, I should really use E here, not 1, right? So, yeah, sorry about that, yeah. So B, alpha B, which is B alpha squared, right? And therefore, this is going to be alpha squared. So we see that that element is already included. So by conjugating by B alpha, we don't get a new element, right? So we now have one left, which is the last element, which was when G is B alpha squared. Of course, from this one, can you guess what G inverse will be?
Alpha B.
Alpha B, right? So G inverse. Let's do G inverse G this time. Okay. So G inverse G is alpha B, B alpha squared. Of course, B squared is 1, alpha cubed is, so I did this identity. Good. So now if I do G alpha G inverse, I get B alpha squared alpha alpha B. And therefore, this is going to be B identity, because these three make identity, alpha of B. So we get B alpha B, which is alpha squared, B squared, which is alpha squared. Again, we see that we don't get a new element. That means this conjugacy class only consists of 2 elements, right?
I have a question. So I just want to make sure that we didn't use alpha cube because alpha cube is already in the previous conjugacy class, right?
Alpha cubed is E, yeah.
Yeah. Okay.
Yeah, exactly. Very good. So we've got the second conjugacy class. Now for the third conjugacy class, we have to pick an element which is in none of the conjugacy classes before, and that is B, right? So now we are looking at the conjugacy class of B. So B is of course going to be there. And now let's do say, let's let G be say alpha, and then G inverse is alpha squared. And then we have G B G inverse is alpha B alpha squared, which is going to be alpha times alpha times B, right? And that's going to be alpha squared B, okay? Now, if we had chosen B to be say B1, then we know that this is going to be B3. Sorry, not this one. This is actually going to be B3. So we can interpret this element as another transformation, which is not in the group, but this is a shorthand notation for this. Okay. So number 2 is, so now we have B and alpha squared of B. Right? And then let's take G to be alpha squared, then G inverse is alpha, then G inverse is alpha squared B alpha.
Sir, the B's commute with the alphas, I think, like, aren't the B's and alphas commutative?
No, they don't.
Or in this case, like alpha square and B, do they commute?
Sorry?
I mean, like, will it be the case that alpha square B is B alpha square?
Sorry, I don't follow. Can you be more?
I mean, like, is there any like alphas or B's that commute? Like, can we have such operations here?
No, you can't, because B will, if you have an alpha, which is a rotation, B, which is a reflection, you know that you're never going to get, in general, they won't. There might be a specific case, like say, if you take for some shapes, they will, okay? And we'll come to that.
This is a non-abelian group, right?
Yeah, but non-abelian groups can have centers, right?
Oh, okay.
And in which everything commutes. And we'll come to that, yeah. So we'll come to an example of the stuff that Nahi is taking. But in this case, of course, these guys don't commute. So alpha squared B is essentially alpha squared, right? Alpha squared B alpha, this is this thing, right? What am I? Yeah, B alpha squared, right? Or let me just So this is going to be B alpha, alpha squared B, and this is going to be alpha of B, right? So this is going to be, then we can give it a name, which is going to be B2. So, so this will be alpha B. Okay, let me just, we can call this. Oh, sorry, it's not a comma there. It shouldn't be a comma there. Yeah. Alpha B. And we have actually exhausted all the elements of our group, but you can still kind of, see if, for the sake of consistency, you can see, okay, what if I take, yeah, I think, yeah. Yeah, actually, we don't have to do anything else, right? So we have actually can close this set. And then we have our equivalence classes, our conjugacy classes, which consist of the identity element, alpha, which consists of a rotation by alpha, and what else? And
so in the B1 equivalence class, we got the element B2 and B3, so we don't need to find B2 and B3.
Well, B2 and B3 are not part of the, right? We are, those are just shortcut names I'm giving.
Oh, so just
right?
one B will do.
Yeah, yeah. I mean, it's just that, it's just for the sake of interpretation, what we're, what we can show is that, okay, the rotations are equivalent and the reflections are equivalent. Okay. So,
yes,
okay. So, you just do this for D4 and you get more. I actually worked this out. I don't have, I think I have the solution somewhere. For D4, I think, did you guys do D4 in the tutorial?
I did. I got 5 of them, including the trivial one.
Yeah, 1, 2, 3, 4, 5. Very good, yeah. And there it's very clear, right? I mean, rotation by 90 degrees is equal to rotation by 270 degrees. And the reflections around the diagonal are equal, and reflections around the other two medians are kind of equal, right? So okay, so let's just discuss the geometric interpretation of conjugacy classes.